We okay to start?
Yes, sir.
Okay. Well, when I left you in part one, we were talking about competency issues, and I just want to finish this off. We use this concept a lot when we go to do channel improvements, and that can be for flood control works, where we want to have a channel with a nice smooth side, nice smooth floor, nice smooth sides. You're going to get greater capacity in a given area, and you're going to get greater competence for moving sediment. On both counts. Now, where this comes up a lot is on bridges. On a bridge, say a box culvert system going underneath an interstate highway, something like that, you're actually going to have a natural channel with a very high roughness coefficient coming in, and then you're going to put it through this tunnel that's a couple hundred feet long going underneath the interstate, and what's going to happen is you're going to get a whole bunch of water piling up and dumping sediment at the upper end of that, and then as it flows through this nice smooth box, the competence and capacity is going to go way up, and it's just going to clean it out, and you're going to dig a huge hole at the end of it. And so what you find is, in that kind of a situation, if we use a universal cross-section, it's not going to be very hydraulically efficient. So in hydraulics, what kills you in this kind of stuff, especially with bank repairs and with bridges, is the change in Manning's coefficient, in roughness coefficient, that you engender when you put an improvement in. I mean, ideally what you'd like to do when you do a bank repair or something is put something in there that's the same coefficient as what's upstream and downstream, and you're going to have less problems on the transitions with back eddy erosion. And so that's tough to do unless you got something really rough like gabions or something, and then when you put the gabion wall in, it's got to be really tight and match the profile of the bank upstream and downstream, or it's not going to work real well. And those things take a lot of finesse, construction-wise and just design-wise, to make them happen. So they don't happen very often. Channel gravels. Channels are grade locally where the conditions are favorable to their deposition. So you're going to see channel gravels being deposited. If you do see them being deposited, what you want to ask yourself is why? Why are they here and over here? And am I on a point bar? In this case, I'm not on a point bar. I actually have a splitting up here going on and some helical flow stuff going on here in a fairly shallow river system. This is down in the Andes in Peru. This is back up in British Columbia, heading up to the Yukon. And here you can see I got huge beds of gravels from the late Pleistocene glacial retreat, melt-off. And so I go miles and miles and miles. I got these clean lag gravels paralleling the river, which is way over here, other side of the valley. And so you have to ask yourself, are these local bars like this, or are these broad deposits going along a large area due to some kind of global climatic shift or base level change? So you want to be asking yourself those kinds of questions. Flood damage. One of the best things you can do is look at before and after pictures to get an idea of the power of running water. It's staggering. It's just staggering. This is a picture along the Santa Margarita River coming out of the mouth of Temecula Canyon down in San Diego County. Before the January 1916 flood, this was a nice, beautiful little canyon. It's tree-lined. This is a steam engine, and that's the steam going up from the steam engine. This is the station down here at the bottom in Santa Margarita, and the water tower here, and this is a whole train. And the train is up here on the terrace, going up the canyon to head over towards Temecula, across the mountains, across the Coast Range. And but this is a confined bedrock canyon. So they had a big flood in January 1916. Now they thought they had a 100-year flood in January 1914, and then 2 years later they had a bigger flood. So that's Q inflation. And so this bigger flood comes down January 1916, and you can see here, it not only just wipes out the canyon, but it takes all the roughness out of it. It takes all this vegetation and trees and everything, sweeps these things out, and you can see the high water lines way up here on the bedrock. And when right here's where you break out of the mountains for the first time in, almost 20 miles, 18-mile canyon. So right here, you break out, and so now the water spreads, and this high reflectance stuff you see all over the place is the sand, and there's pieces of railroad rolling stock, box cars and stuff, just hither, skither all over the floodplain. This railroad never got rebuilt after this flood. It just completely wiped it out of the canyon. And that's what one kind of event can do. Now, the other thing I want you to look at is here's those fringe deposits going up the sides of the canyon. These are sands deposited around these few trees that are still left along here. So you see how that stuff gets deposited up here. So if you see sands up here in those kind of positions up on the side slopes, you know they've had a major flood in the recent historic past. Not just the recent geologic past, but the recent historic past. And you want to find out more about that flood. In fact, if you trench it right in this area, you could find out about this flood and about the previous floods to try and get a recurrence frequency on how often they get water getting up that high. That's pretty amazing. And you can see down here in these trees, the bottom 20 feet just stripped off. And everything's just, the buildings are blown away, the water tanks got all kinds of damage. And it's pretty amazing what one storm event can do when you see one. Another great area that I used to see in practice all the time was channel constrictions. We do this to save money. We're trained as civil engineers to save money, save money, save money. Do it the cheapest you can possibly do it. If you have a seemingly small, most of the time dry channel, then encroach on the channel with approach fills. Put in a concrete abutment wall, and then put a much smaller bridge across here. And that'll carry your 10-year flow, and everything's smaller than the 10-year flow. But when you get to something like the March 2nd, 1938 flood, which was probably close to a 100-year event in Los Angeles, San Bernardino area, here's what happens. The water squeezes through this little opening you've left here. It digs a really deep hole, because Q equals V times A, and it back eddies and removes the approach fill pronto scanto. The approach fill's gone. You get a major event, you got an approach fill going halfway across the channel, 2/3 of the way across the channel, you're encroaching the 100-year channel, is going to be gone if you have any kind of duration. Now, this was not a long duration storm by any stretch. It was a relatively short duration storm, just a day and a half, but they had every bridge in Los Angeles and San Bernardino County was either destroyed or severely damaged. The only bridges that survived that storm were some of the bridges on the Los Angeles River, not the railroad bridges. They got taken out. But most of it was this reason. Most of it was because they had used approach fills, because they're in a semi-arid environment. The channels don't have much water in them, perennially speaking, year-round. And so you can do this kind of thing, but what's going to happen when you get a 75 or 100-year event, you're going to lose it, because these things weren't even armored. Now, the most vulnerable side of the embankment, the down gradient side, not the upstream side. The down gradient sides where you get the back eddy scouring after you go through the narrow opening under the bridge. Back eddy scours. So when you go out in one of these things, you're watching the flood, your tendency as an engineer is always to be looking upstream, see what's coming downstream. Be careful. Check your six all the time. Look behind you, because the side you're going to get killed on, and it happens every year out west, is the downstream side. That's where it gets taken out from. It gets taken out by back eddy scour motion on the downstream side. Okay. Flash floods are what we get in arid and semi-arid areas, desert areas. This is Palm Springs. And this is what happens when you have a short-term event, and you're going to get lots and lots of turbidity. It's very, very turbid. It's going to pick up anything that's cohesionless, silt and sand, and it's going to keep that in the channel and move it through here very, very rapidly. And so the best way to combat this is with an Arizona dip. You see that right here. They have a concrete apron that dips down, goes underneath the channel, and then back up on the other side. This is a golf course down near Whitewater Wash, Palm Desert area. This is how same thing they deal with in Arizona. That's why they call it an Arizona dip. It's infrequent enough, these type of flows are infrequent enough that you just come in here and clean it all out later, and you just accept the aggradation in the channel, and you have to live with it and work with it because the cost of diking this thing and putting clear span bridges is colossal compared to how often you might use them. You might only use them once every 10 years, something like that. And so people don't feel like it's a cost-effective thing to do. And so this is very, very typical of the kinds of damage we get in the Southwest. I had one in the Coachella Valley Water District where the channel like this ate down 17 vertical feet in one event, coming on the transition coming out of the mountains, coming into an alluvial fan. And boy, you can get a lot of erosion in 24 hours in that kind of environment. There's no cohesion in the material. Okay, that ends character of channels. Let's move on now with the next section. And that's going to be classic floodplains. What do I want you to know about classic floodplains? Most of you have seen these kind of diagrams in your physical geology texts. Classic floodplain is the bank to bank between these terraces. This whole area can flood, and then we can get terraces, inset terraces, within the floodplain. Those are actually very, very common. And 75% of the sediment deposited on the continents, on all 6 of the non-frozen continents, is silt, floodplain silt on major floodplains like the Mississippi River. You can't compare anything with it. I mean, just in terms of volume, in one event like the 1927 flood, the lower Mississippi River, you had inundated areas that are almost 100 miles wide. And then you're putting in there, 5, 6, 7 feet of silt over that large of an area. That's a colossal amount of sediment. So it's mostly silt. It looks like mud. Everybody calls it mud. Everybody calls it clay. But if you get a little bit, put it on your tongue, it's a little gritty. That's silt. Floodplain silt is what comes out of the river. Now, the further away you get from the river, the finer grained typically the material is, because you're in lower energy environment in the slack water deposits. You get slack water deposits over here on the edges of the floodplain. Here's what's going on when you have a river in flood. You have something looks like this. If it's an ideal, straight section, it looks something like this. And when the water comes up, it reaches its greatest efficiency right there. That's where the hydraulic radius number is the most favorable. The ratio between the volume, cross-sectional area flow, and the wetted perimeter, it's most efficient for transporting sediment right to there. Now, when it comes up like this, it also deepens itself at the same time. But as soon as it gets up to the top here and spills over this lip right here, it spills over, what's going to happen on this spillover is you have a lot higher roughness, and you only got like 1 inch of water when this thing starts to come over. So your ratio between Q and roughness is suddenly, order or 2 orders of magnitude greater than it is out here in the slicker than snot on a doorknob, channel. And so what happens is the sediment, suspended load, starts dropping out because velocity drops dramatically going in this direction as compared to going straight down the channel. So what happens is you build up natural levees like this. And this is what you see on all alluvial systems. Alluvial systems are channels with hydraulic grades less than 1.5%. So they drop 1.5 feet per 100 feet or less, you're an alluvial environment. And so something like a Mississippi is alluvial environment virtually all the way up into Minnesota. So what you end up with are natural levees that look like this, that are the high ground, and a floodplain with floodplain silts out here on lower ground below the natural levees. Now, this is what General A.A. Humphreys observed in his landmark study for the Corps of Engineers back in the early 1850s. And he was a West Point trained mathematician. And his mistake was he looked at it like this, like a class. and said, well, if this is what the channel looks like, if I put levees right here and heighten this, I take some of this silt right here, drag line it up, and make the levees higher, now when I have a flood, I can bring the flood way up to here, and this will dig down deeper. And that is the most inexpensive way I can train this thing and keep it from flooding everybody out who lives over here on the floodplain, places like Memphis. Now, what's wrong with that? Well, what's wrong with that and why it didn't work, the levees only program, 1877 to 1931, it didn't work because it was a two-dimensional representation of a three-dimensional situation. In other words, the Mississippi River doesn't look like that anywhere except in geology textbooks and channel hydraulics textbooks. What does it look like? It's an asymmetric channel. So it never looks like this. What he's doing here is he's ignoring curvature and asymmetry. And if you fly over the Mississippi River, the one thing you'll come away with, if nothing else, is one, it's muddy, and two, it's serpentine. It's moving around like a bunch of intestines. And it's got all these oxbows and cutoffs all over the place, testifying to how dynamic a natural system it is. The larger the river, the more dynamic the system. You look at something like the Mississippi or the Danube River in Eastern Europe, wow, those systems are incredible for how dynamic they are, how much the channel can move around. One storm, the channel moves 10 miles across the floodplain. Wow, that's scary if you're the engineer, trying to save everybody. So this levees-only policy didn't work because of the curvature. And one side actually ends up being a lot steeper than the other side, and so that side fails through bank undercutting. You lose the levee here, and voila, the flood's all over one side of the floodplain pretty quickly. And because the river's so serpentine, it gets around to the other side as well. So it didn't work. Now, what you could do is you could put training dikes right here, and then you'd have a setback levee back here somewhere that would protect your high-value property or developments over here. That way you don't put the one that really counts, the high value setback levee. You don't want to put that thing right next to the channel because you're putting it in a point of greater vulnerability. They just use common sense on that. So setback levees, a real good idea, and then you use training levees, dikes out here near the active channel, which you sacrifice the training levees during the big flows. And you realize you're going to lose them, but you're not going to inundate everybody's neighborhood if you have the setback levee there for the safety. So here's a picture. Here's what we're looking at along the Mississippi River, 1913, one of the first big comprehensive reports in the 20th century. We look at the Mississippi River at Belle Point, Louisiana, and what do we see? We see the river up here as the high ground, and then we see everything else trailing off below it. You look at a map of Missouri, and you look over here in the southeastern corner of Missouri, and there's the Mississippi River leaving the state. And everybody assumes that's the lowest point in the state, and you'd be wrong. You'd be wrong by 30 feet. That river's 30 feet higher, actually, than the St. Francis River, where it leaves the state of Missouri on the other side of the boot heel, 30 miles to the west. Because it's a bigger river. Bigger rivers, more competence, more Q, more silt. More silt, they dig up a higher mound, and now you see the problem for flood control. Here's your natural levees poking out right there. But if the water comes out here, what happens? It's got a real nice, healthy hydraulic grade, which means it flows downhill, and this slope is much steeper than the slope of the river. So when it breaks through here, it breaks fast, and it comes down with a vengeance and cuts a hole, and it gets out here to the swamp area, lickety-splitsky-ditsky. Doesn't take any time at all. Foosh! Because you got drop, hydraulic drop. In the case of Mississippi River, it's about a 30-foot drop across the floodplain. That's plenty, even over a couple miles. That's way higher than the gradient of the river. I mean, this river, drops very, very low gradient as you get down below where the mouth of the Ohio River is. And so if we look at the types of sediments we would expect to see now in this environment, here's what we're going to see. We're going to see point bar sands and gravels historically back here where the active channel has been in the late Pleistocene, early Holocene. And then we see the Holocene channel sands right here. And the levees and the bed of the river are very sandy. But as we get away a short distance, a few hundred meters, that starts getting finer. So you get finer sand, then you get into silt, finally you get to clays, and out here in the marsh, yuck, it's like a sewage treatment plant. What does that mean? Peats, clay, and something they call organic ooze. You don't want to know what organic ooze is, but if you ever had a baby that had diarrhea, that's kind of what it's like. It's a very soft, it doesn't have shear strength, it doesn't have bearing capacity. What it has is it's a brown and it's liquid and it doesn't smell real good. This is not real great stuff for doing much on at all. So that's why it took 150 years till after we built the Panama Canal and we had drag lines and large kind of earth moving equipment. They came along and made drainage districts, and they dug huge ditches out in these areas so they could drain them, so they could do agriculture in them. So that agriculture didn't even start till after the First World War. So it's post-1918. And between 1918 and 1940, the Little River Drainage District down in southeastern Missouri, just based out of Cape Girardeau, moved more earth than the Panama Canal project. Now, the Panama Canal, they moved 96 million cubic yards of material. They moved 116 million cubic yards of material just putting in drainage ditches for the Little River Drainage District. Why? Well, because you got a million acres. So we reclaimed these floodplain areas that previously had not been good for much of anything because they flooded every year. Every year in the spring flood, Mississippi would break somewhere and store these huge floods out here. And it was a big, huge loss of irrigable land. So man conquered nature till the next big flood came along, and then nature conquers man. All right. Well, here's what I'm talking about. Here we are going along, lower Mississippi embayment. We got this serpentine channel. It's not straight anywhere, not for very long anyway. It's snaking around, and it's the high ground. And you have these back swamp areas that have very poor drainage. Sometimes you get a Yazoo tributary that eventually coalesces into a channel, and way downstream somewhere, like at Vicksburg, the Yazoo River comes back in to the Mississippi. But when this thing floods, and that's the high ground, the channel's the high ground, here's what happens. The whole darn floodplain becomes a swimming pool. Not part of it, not the right part, the whole thing goes underwater. And this is what happened along lower Missouri River and middle Mississippi in the 93 floods. You just saw the whole entire floodplain, cliff to cliff, miles across, goes underwater, and it was underwater the whole summer. So that's the problem you're battling with when you try to dike these things off and protect these developments that have been put in here and there selectively. It's a big, big challenge geologically. That's a huge challenge. I can't trivialize it at all. This is as big a challenge as the Dutch trying to take the mouth of the Rhine, and polder it off. And they had to spend 35% of their gross national product of that country for 30 years to do that. So you have to have the political will to do that. And that usually comes after you have a major flood like they had in 1953. And it has to be a major flood that wipes everybody out and kills a lot of children. Then you get action. You get political resolve to do something. Here's what I was just talking about. Here's an ERTS picture, Earth Resources Technology Satellite picture. This is the lower Mississippi River. This is the Illinois River coming along. This actually used to be the main stem of the Mississippi River prior to the Illinoisan glacial break, and then it moved over here about 200,000 years ago. And so this is a very youthful channel. It comes down, they join back together here, and then they come down here towards St. Louis, and this is St. Charles, and this is the Little Muddy. What's the Little Muddy? The big muddy, that's the Missouri River. And there's what it looks like most of the time. Not a whole lot of water. And there's the junction. And there's St. Louis. So there's the confluence. Look what this thing looked like in the 93 flood, through the summer of 93. And what's going on here is you have the Missouri River in full flood that entire summer, late spring and summer. And then you get down to places like this, near St. Peter's and St. Charles, and you got dikes protecting the development. St. Charles predates St. Louis. And so you got dikes here, you're narrowing the water, and so as you join this other river here, you have a backwater effect. And that's what you see damming these other things up. They're backwatering and washing out all the Army Corps of Engineers locking dams, going upstream here for quite a ways. So this system comes around, and then it hits the improvements around St. Louis. St. Louis is protected. Look at the backwater in the Merrimack River right here. Very significant, coming down. Merrimack River actually used to be a pour-over point at Gray's Summit here. This used to be a big ice dam right here near Chain of Rocks. So during the ice ages, the Missouri River used to actually flow over here, and it cut this big, huge channel of the lower Merrimack River that looks so out of place because it doesn't have the watershed area to have cut that big of a channel. You have a 150-foot deep alluvium in Eureka Valley, and that's because of the glacial pour-over that occurred in here and comes down like that. So, wow, that's, you see something like this and you realize, whoa, baby, what are we dealing with here? We're dealing with a tremendous amount of water from the normal everyday to what happens when you have a large event. All right. So the big thing I want to leave you with as a geological engineer is channels are asymmetric, asymmetric, asymmetric. You show me a symmetric channel, you're showing me a textbook for freshmen. Okay? Channels are not symmetric. Hardly ever. That's a once in a blue moon type thing. The channels are asymmetric, and because of their asymmetry, they tend to have retrogressive sliver failures over here on the over-steepened banks. And especially when they get high flow, and they start having problems, they scour out, and that's enough of a problem just for undercutting. You're going to get some stuff that falls in. But where you get this retrogressive slumping, like you see right here, this is actually down near New Orleans, this is from the flood stage dropping down fairly rapidly. And when it drops down rapidly, you get a rapid drawdown condition, and then boom, you're off to the races. You get one sliver, then another one, then another one. And we call that progressive failures or retrogressive failure. Bank undercutting is the colloquial term given to it. But you can see bank undercutting is going to get the dike that's right next to the river. So you don't want to depend on a dike right here on the outside of a turn. That's a training dike. That should not be your last line of defense, unless you got a boat factory over here and you like to swim. What you want to do is put a training dike in here, but then you want to have a setback levee back here in a safer position, because this thing is gonna fail at some point down the road. All right. Low gradient channels love to meander. And when they meander, they have asymmetry. They're steep on the outside of the turn, and then they switch back to the other side. Then they're over-steepening over here. So they got bank lossage going on here, got bank lossage going on right there. And as this thing continues to have bank lossage and migrate and move, it moves outboard and downstream. So it moves out and down, and eventually you're going to get a neck in some place like this. And when you have a neck here, during some large event, you're going to get a breakthrough there. And when that breakthrough occurs, you're then going to have a very, very high gradient that's very short-lived. This is going to break through here very rapidly, and then it's going to actually move around some in relationship to that. This gets cut off and becomes an oxbow. It plugs with silt, and it sits there for a long, long time as an oxbow lake. And the only thing that's going to fill up an oxbow lake is then repeated flooding of the entire floodplain. And gradually, this thing is going to fill in with jello. It's going to fill in with organic silt. That's going to take a long time. Then you put artificial fill over it, and you'll wonder why half the building's settling and the other half isn't, because you're on an old oxbow. So oxbows are a huge pain in terms of geotechnical hazards. You know, if you have part of an interchange on an oxbow and part of it's not an oxbow, obviously you're going to have very, very contrasting conditions for foundation support. So, low gradient streams are the most problematic because they're the most sinuous. So they tend to do pinch-offs and cut-offs much, much more regularly because of their low gradient. So oxbows and cut-offs are common features, and they're very treacherous because of these changing foundation conditions that you have across here. You can see there's an old channel right there that's gotten filled in, and then the more recent channel over here. So if we look at a map, this is the Corps of Engineers engineering geologic map of Mississippi River, right where the Ohio River flows into the Mississippi River, near Cairo. Now, the active river is shown in white. That is the active, stabilized river that the Corps took ownership of by congressional mandate back in the Flood Control Act of 1928. And so the Corps started looking at this thing and trying to keep it in one place for flood control and navigation purposes. And what you're seeing in blue are the historic wanderings of the Mississippi River, just going back to the time of Mark Twain, last 200 years. Look at these things. This thing is all over the place. And then you go out here further on the floodplain, and what is all this hot stuff? It looks like flames. Those are braid bar gravels from the Pleistocene, late Pleistocene melting of the glaciers. When sea level was 360 feet lower, the river had a much steeper gradient. Steeper gradient means more competence. You can transport larger material. So all these braid bar gravels are from when the Mississippi was flowing 300% of the Q you see today. It's much, much higher Q on a steeper gradient, and you'd never get this stuff today. This stuff is underlying the whole city of New Orleans. Anywhere from 75 to 150 feet deep, you got lag gravels. Gorgeous lag gravels. Ain't no gravels anywhere in the state of Louisiana that are exposed. They're all buried under the Holocene. So you have to have deep piles going down into them. So we can use these for aggregate sources. Of course, they're not great for agriculture because they're not fine-grained enough. They lose water pretty quickly. But what a dramatically different material here than these floodplain silts in the chocolate color. And you can see how these channels are just pinched off and truncated and very, very complex patterns. Very three-dimensional. Okay. That's the one thing I want you to remember. Very three-dimensional. And so be careful when you do all your analysis using two-dimensional cross-sections. Those are greatly oversimplifying the actual situation. Okay, that closes part 6. Part 7 is channel form and patterns. All right. One of the concepts we talk about in geomorphology, or the study of landforms, is antecedence and superposition. So what do those things mean? Let's look at the definitions. An antecedent stream is one whose path of flow within a valley was established before the mountainous structure was uplifted. And we see that kind of stuff like here. We have this, sinuous, kind of looking like a mini Mississippi, and that was developed on a shale unit, on a very low gradient. Then the land lifted up, like the Grand Canyon, and the river just eats straight down. And so you end up getting this low gradient channel form on top of a rejuvenated landscape. So that's antecedence. Superposition, superimposed streams, are one whose valley and direction of flow were developed later, much later than the underlying structure. And the river possessed sufficient stream power to cut through these underlying structures. And this is a lot of what we have back in the Appalachian, Allegheny, Great Smoky Mountains uplift. In fact, we even look at the French Broad River, which runs through Knoxville, Tennessee. It goes all the way through the heart of the Great Smokies, which go up to 8,000 feet, all the way over to Asheville, North Carolina. So that water's coming from over in the Carolinas, coming across that mountain range and heading over to the Ohio River and thence into the Mississippi River. So that's superposition. And that's why you get things like wind gaps sometimes where the river couldn't keep up, so we're going to see. Okay, so what are some of the common drainage patterns that are structurally controlled? This is geologic structurally controlled. Not like structural engineer structurally controlled, but similar concept. If you had a homogeneous kind of material, rock or soil material, you tend to get a dendritic drainage pattern. And as you get smaller and smaller watershed, lower and lower order channels, so you're starting out third order, fourth, third, second, first order, this is going to be dendritic-like. And that's the most common one that we see worldwide. Where we get away from that is if we have carbonate rocks, like in a karst environment, like around here. We'll actually see rivers do right turns and left turns all over the place because they're following systematic regional joint patterns. So we have a semi-rectilinear pattern around here. We also have a superposed older river system here. But we see when we get further up in the watersheds, we actually see the rectangular controls here and there. We can actually see some of these right turns and left turns even in some of the major rivers around here. Aside, not talking about the Missouri River, but rivers like the Gasconade and the Merrimack. Now, when we're structurally controlled, trellis drainage is where we have a combination of folds and bedding and structure that's actually exerting control on the channel. And that's what you have in most of Pennsylvania, places like the Allegheny uplift. It's definitely a trellis system of synclines and anticlines. It's a big fold belt, and that impacts the channels. Here's a channel coming down a syncline system and then meeting the trunk stream. The trunk stream here is superposed. It was here first, and it's pushed through these hard gaps as the land's lifted up. So it's pushed through those gaps. And you have these resistant ridges from the folding. These are the resistant rock units. Typically dolomites, quartzites, things like that. Sometimes sandstones if they're well cemented. Radial is what you get around volcanoes. It's a very, very unique to volcanic situations. We do have those out in the Pacific Northwest, in the Cascadia volcanic field, which starts out way up at Mount Baker at the Canadian border and goes down to Mount Lassen in California. All right. What's a water gap? We hear that term water gap gets used. Water gaps are where you have an existing drainage system developed on flat-lying, soft sediments. Let's say it's a dendritic system like you see here. And now the land uplifts. We have the Allegheny uplift. And here we have sufficient stream power, like the New River Gorge over in West Virginia, coming out of West Virginia into West Virginia. That's going to play on words there. Flows north, and it goes through these incredible water gaps, these canyons. That's because it had enough stream power to eat through this resistant, like a dam. It actually eats through that on either side and comes through. And so you have perturbance of all the feeding tributaries by this later structural control down here. But a lot of the older main trunk channels are going to continue going where they went because you had enough water going through it. So that's called a water gap. It becomes a wind gap when it gets pinched off and there's insufficient stream power to keep pace with the uplift of that resistant unit. And so here we get stream piracy. Another channel comes over and pirates this watershed, and it leaves you a wind gap. The Cumberland Gap, which was the great thoroughfare between the eastern seaboard and the Ohio Valley, is one such wind gap on the upper end of the ancestral Potomac River drainage. So see here, you have a water gap here, water gap here, but when you got up here, this water gap later got stolen away through piracy, and that becomes a wind gap, and the river turns and goes another direction. So actually these things have been mapped out pretty well all through Pennsylvania, Tennessee, the Carolinas, and the two Virginias. Okay. See if I can get the next one done here for you. Part 8. Alluvial deltas and fans. Now, there's a lot of things I want to tell you about alluvial fans. One is they're usually not alluvial. Usually they're deposited by debris flows, debris events. Then they're reworked by the water that comes down and reworks the debris fans. But a classic alluvial fan looks like a fan when you fly over it in the air. And it develops where you have confined bedrock channels coming down and breaking into a broad sloping region like a valley. So you get this sudden dispersion because this flow, which is confined, now can spread. As it spreads, just like that water coming up out of the Mississippi River, as it spreads, you now have a much shallower water depth and very high roughness, so you deposit your sediment. Your sediment comes out and decants out of the mixture. When we look at deltas, it's a similar kind of phenomenon, but here we have controlling base level. And so this sediment-laden water is coming out here on a very, very low gradient and pushing. It has to push against the ocean, and the closer it gets to the ocean, the more pushing it does. And the only reason it's even able to win the battle is because the sediment makes that fluid heavier than the seawater. Seawater is about 1.03 times density of clear water, but this supercharged sediment coming down here is coming down at like 1.35. And so it's able to win the tug of war and push this sediment into the Gulf. And what you get is this prograding cross beds coming down about 30 degrees that just keeps pushing out, pushing out, pushing out. You get these four-set beds with the bottom set beds out here in front of them, which are the turbidity channel deposits. And so you're laying this thing out there very, very rapidly. Now, the Birdfoot dike that we see in New Orleans, below, downstream in New Orleans and Mississippi River, that thing is really young. I mean, that whole thing's been thrown in there just in the last 2,000 years. I mean, and most of it 1,000 years ago. So that wasn't even there 2,000 years ago. If we look at the Mississippi and Chafalaya rivers, and we look at these deltas, they've actually gone back and dated the various deltas here. And you can see delta number 7 is the oldest. So delta number 7 is the one that's way out here. Excuse me, delta 7 is the youngest. This is the one that just came out here where the modern delta is. And number 1 is the oldest, and that's the Chafalaya. And number 1 actually has much, much thicker sediment accumulation than over here. New Orleans is actually sitting way over on the distal east end of the delta, right there. Middle of Lake Pontchartrain, the distal east end of it. So it's way over. The depot center of this delta is over here in this area. So very, very fascinating. And also, the water that comes down the Chafalaya has 1/3 the distance to go that the regular Mississippi has to go. So if the river ever breaks out up here and comes down the Chafalaya, it's going to cut one heck of a canyon in a couple hours. 24 hours, all going to be over. And all the water is going to come out of there. That's called the Old River Control Structure. And it did fail in 1973, but they didn't have a catastrophic failure. They had an undercutting of the hydraulic control structure, but they didn't lose it because it was on battered piles. And so they built a new one there next to it. They more than doubled the capacity, but the river would cut this thing in a flash because that's a shorter distance to the Gulf, right down here. Boom. It's 1/3 the distance of taking the current route, which is very serpentine, all the way out here. Now, if we look at the abandoned distributaries in the Gulf, here's the modern Birdfoot Delta, where Eads put his jetties, starting in the late 1870s. Here is New Orleans, right there between Lake Pontchartrain and the river. And what I have highlighted in red there is the Metairie Gentilly Ridge, which is a very prominent discontinuity or a distributary channel. It's about 5-6 feet above the floodplain around it. So if you're lucky enough to live on the Metairie Ridge, when they have big flooding like Hurricane Katrina and Rita, you didn't get flooded out if you were along that ridge. You're up higher. So all of these ridges, these are ridges you see here. This is all ground that's slightly higher because of sedimentation than the swamps between it. So the channels are the high ground, the swamps are the low ground. And that's why when you go down here in Terrebonne Parish and you try to build an 18-foot high, 100-year flood dike, it's got to be about, 1,500 feet wide with 1 on 16 slopes, and even then it's just sinking into the peaty soils of the swamp, and you just have to keep adding and adding and adding, and it keeps sinking and sinking and sinking. And it's a good deal if you're getting paid by the yard. I mean, you're going to have a lot of work there. You're just going to keep feeding the things, feeding the monster. Now, until we had the construction of the jetties by James B. Eads in the late 1870s, when you had low flow of the river, you would have insufficient stream power to break down the bar sands that would form. We had the same problem in San Francisco Bay, too. Until came in and did some engineering to keep it cleaned out, because you're going to get bars forming down here during the dry season, and you can't go upstream. And that was 3 months at a time every year, usually in the late fall and winter months. Okay. Now, what I want to tell you is we have this. You have 2 weeks. So you've had 1 week so far to do the Chapter 8 homework. You're going to get another week to finish that homework, and I am posting your midterm on Blackboard for you to take, and you have a week to do the midterm. So both assignments are going to be due the same time, which is going to be Monday, November the 8th. So Monday, November the 8th, I'd like to see your take-home midterm, and I'd like to see your questions on Chapter 8. Now, if you can't finish the questions on Chapter 8, send me a promissory note. Tell me why and when you do promise to get them to me. Yeah, I'm a reasonable man. I'm just like the boss at the office. What I want to hear is honest and truthful communication. Okay, that's all I have for you today, and I'll look forward to seeing all of you again next week. Thank you.